Hey guys, welcome to another test video. Today we're doing trigonometry, the non-calc section. Like the last test video that I've done, this is just going to be pretty much stream of consciousness, running through each question as to what I'm thinking and how I'm doing it, and trying to discuss any kind of common errors that I might be familiar with so that we can try and prevent those. Okay, let's get started. Question 1. Use the unit circle below to determine the approximate value of the below to 2 decimal places. So that's supposed to be an S there, 2 decimal places. Okay, so we have a unit circle. We've got a nice grid going on here, and it looks like that it is, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We've got a scale diagram of the unit circle with a 10 block grid here, so each one would be 0.1. Remember, the radius of your unit circle is 1. Over and around the side here, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 dashes around the edge of my circle. Each one of those dashes has to be 10 degrees. Okay, so sine of 40 degrees, we are thinking about our unit circle. Any point on my unit circle, yes, let me do side view notes here. If I have my unit circle, okay, any point on this unit circle can be described as x, y, or as some description from your theta here, cos theta, sine theta. Your distance here is cos theta, your x distance, and your height there is y, or sine theta. This is cos theta. So x, or your cos theta value, is the x value on the coordinates of your unit circle, and sine is your y for the coordinates of your unit circle as that point travels around. And this explains a lot about our trigonometry stuff, so we'll come back to the unit circle quite a bit in this video. Sine of 40 here. I need to know what 40 degrees is, and I'm going to use a trusted ruler to help me out. 1, 2, 3, 4. Okay, connect it with the origin here. That's 40 degrees. Okay, and sine would be the height at that point. So what is this height here? Okay, that height is 1, 2, 3, 4, 5, 6, and about a half. So approximately 0.65. Okay, we're supposed to be going to 2 decimal places. You might say 0.64 or maybe 0.63, but we'll do that. 0.65 now. And this is a calc free section, but it would be nice to demonstrate that sine of 40 degrees. Just make sure that it's in radians. I need to change that. Better. Sine of 40 degrees, the approximate value, 0.64. Okay, so we did pretty good based on a scale diagram. Cos of negative 80. So when you are measuring your angle, it is always from the positive x angle up, positive x axis, and then in an anti-clockwise fashion. Unless it is negative, you want to be going the opposite way. Okay, so 10 degrees less than 90 is about there. if it is negative 80 here, we're going anti-clockwise 80 degrees. Oh, sorry, clockwise 80 degrees. Anti-clockwise is the direction that we normally go. Positive is that direction, negative clockwise. Alright, so we need to tell the x distance here. Okay, so the x distance there is about 0.1 and not quite 0.2, let's say it's about 0.18, and it is on the positive side. So again, this is just for the benefit of the video. 0.17. So again, we were pretty close to the actual value. Alright. The idea sine is y, or height, y coordinate, I should say, and x, cos is your x coordinate. Tan is a little bit trickier, and I might even do this in a different color. Okay, it's hard to tell on both the test and in the video, but there is a tangent line going down here. Alright, still hard to see. Maybe if I highlight it. No, probably not. Still hard to see, but that there is the tangent. Alright. For tan of 160, alright, we are trying for 160 degrees, which would be about here. And we're trying to see where this line extended out touches that tangent. Okay, so what is that part? Okay, it is below the x-axis, so it's negative. Alright, and it's about 0.1, 0.2, 0.3, 0.35. Go halfway through, and for the sake of checking for the video, tan of 160. I'm going to keep doing that on it. Negative 0.36. So you can see, based on our scale diagram, you don't have to be perfectly exact for these answers because it is a scale diagram and a small one at that, that there is a little bit of room for error in the answers for here. So you may have said 0.65. That would still be correct, even though the actual answer is 0.64. Right? Same with these two. A little bit of room for error. But what we do need to make sure is that we understand that sine is the y coordinate on my unit circle, and cos is the x coordinate of my x coordinate on my unit circle. Tan is a little bit different because I am actually thinking about where this extension of this angle here, okay, where that hits the tangent on that side. Okay, there are other ways to think about tangent which moves with the angle, but I feel like this is easiest for what we're trying to do here. Alright, question 2a. So firstly, solve the following conversions, simplifying where possible. Express 30 degrees in radians, leaving your answer as a multiple of pi. Okay, so we're trying to convert degrees to radians. So to do that, we are timesing by pi and dividing by 180. And that is just a conversion factor that we're going to need to remember, okay? It gets you, the way that I think about it is that if I'm converting to radians, then I'm timesing by pi. If I'm converting from radians, so back to degrees, then I am dividing by pi. And we'll get to that in parts C and D. Now, 30 times by pi on 180 is 30 pi on 180, but we need to be able to simplify. So what number divides both 30 and 180? Well, 30 is a pretty good number there. 30 divided by 30 is 1. 180 divided by 30 is 6. So 30 degrees is pi on 6. Being able to simplify fractions is a skill that we should be either practicing if we don't know, or we should know by now. Okay. To B, we are expressing 200 degrees in radians, leaving your answer as a multiple of pi. Part A should be an angle that we're familiar with, 30 degrees, pi on 6. It's one of those exact values that we use quite a bit. 200 degrees, however, is a little bit different, but it works the same way, timesing by pi and dividing by 100. So I get 200 pi on 180. I am not timesing both the top and the bottom by pi. I am just, when I'm multiplying fractions, multiply the tops, multiply the bottoms. There is a 1 there, so we don't need to worry too much about that bottom line there. So then I'm simplifying 200 pi on 180. What divides both 200, or what is the common factor between 200 and 180? 20 seems pretty good to me, but you might start with the zeros. Okay, 200 divided by 20 is 10 pi. 180 divided by 20 is 9. You could do that in more steps, as I said, but that's about as simple. That's the simplified fraction that we could get. All right, express 5 pi on 4 radians in degrees. Now, it is easier if we recognize the size of the fraction first, okay? We might remember that pi on 2 is 90 degrees. So anytime you've got a fraction of 2, you're counting by 90 degrees. So something like 3 pi on 2. This part tells you it's 90 degrees, so this is 3 times 90, or 270 degrees. Same with pi on 3. Pi on 3 is 60 degrees, so something like 5 pi on 3 is, well, that tells me that's 5 lots of 60 degrees. 5 times 60, 300. Pi on 4 is 45 degrees. Pi on 6 is 30 degrees. And occasionally, even though you're unlikely to get it, pi on 12 is 15 degrees. But these are the ones that our exact values come from, the ones that we use most often. Anyways, so look at the denominator, and it's going to tell you the size of the fraction. So here we've got 5 pi on 4. Pi on 4 is 45 degrees, so I've got 5 times 45. Okay, 2 lots of 45 is 90, 4 lots is 180, so 225 here. Okay, 180 plus 45 is what I'm doing in my head. The other way to do it is to think about 5 pi on 4 times by 180 divided by pi. Pi's are going to cancel all the time, so I'm doing 5/4 of 180, and I would recommend you simplify first. Okay, so I can divide both 180 and 4 by 4, making this 1. 180 divided by 4 is 16 is 40, so 180 must be 45. 5 times 45 is equal to 225. Same idea, but I reckon it's easier to remember the denominators and pair them up. So pi on 6 is 30 degrees. We've got 11 lots of 30 degrees, or 330. Other way, pi on 6 times 180 on pi. Pi is going to cancel always. If there's a pi there anyway. So you don't have to do the 11 times 180, which I've seen a lot recently. You simplify the fractions first. 180 divided by 6. Well, that goes 30 times, and then I'm back to this side of things. 11 times 30 is 330. All right. Question 3. Find the exact value of the following. Sine 90. Well, A is sine 90, B cos 210, C cos of 2 pi on 3, and tan is 5 pi on 4. Now, with your unit circle, which is very important for your trig values, okay, most of the time we'd be working within, not even most of the time, but we usually consider this triangle here within my unit circle. Alright, in the positive quadrant, where all of my trig functions are positive. X and y are both positive, so X and y is positive. X, y are both positive in that first quadrant. Okay, so cos and sine are both positive. And if you've got two positives, remembering that tan is sine on cos. You've got a positive divided by a positive, so tan also has to be positive. Anyways, we can remember our acronym, all stations to central. Okay, and then from there, we are considering congruent triangles, always measuring the angle from the x-axis. So thinking about this bow tie, I think it's been described to me once before, where we're always thinking about the angle from the x-axis, and we've got 4 different triangles. They all have the same they've got the same height, okay, but sometimes it's below the y-axis, sometimes it's above the y-axis, and they've all got the same x value, but sometimes it's on the negative side, and sometimes it's on the positive side. Remember that this is on the Cartesian plane. That's x, that's y. Okay, so positive x, positive y, negative x, negative y. Alright, which is where your all stations to central comes from, because it's where your x and your y's are positive or negatives. Regardless, we're thinking about this bow tie formation. Angles within this, or angles always measured from the positive x-axis. So, in that regard, okay, that's what we're going to use for parts B, C, and D. Side of 90 is a little bit different because we're actually thinking about, going back to the unit circle quite a bit. It is something you need to get a good grip on. At 90 degrees, I'm thinking about the coordinate on my unit circle, and x is my cos, and sine is my y. So remember that the radius of a unit circle is 1, that's why it's called the unit circle. Alright, so I have a height of 1 and a x value of 0. Alright, so cos 90 is 0, sine of 90 is 1. So we're considering what the angle is and then what the coordinate is at that point. Because we're thinking about sine, we're thinking about the y value. Sine of 90 is 1. It is the height at 90 degrees in my unit circle. Okay, cos of 210, quick sketch. I'm trying to think about where 210 is. 210 is bigger than 180. It's about 30 degrees bigger than 180. Okay. ASTC. Because it is not in my first or fourth quadrant, as we label them first, second, third, fourth. I know it's tiny writing, but we'll get back to that. It's under the first or fourth quadrant, so cos has to be negative. It's left of the y-axis. But what acute angle do we have to be thinking about? Well, it's the angle measured from the x-axis. In this case, it is 30 degrees. That triangle is the same, has the same x value as the positive 30 degrees on this side. Same distance here. They're the same triangle, just flipped or rotated around the x and y axis. Okay, so cos of 210 is negative because we're in the third quadrant. Cos of 30, because 30 is the angle that is made with the x-axis. Okay, if we can recognize that much, which is great, then we need to make sure that we remember our exact values for sine, cos, and tan. Now, there is a video that talks about hand values, so you can go, it's probably going to look weird in the video, but cos of 30, and I don't really practice it, 0, 30, and then I'm counting the fingers above the top, and then it's over root 2. I'm a little bit unsure. I remember it slightly differently. There's videos out there, so please look them up if you're interested about the hand thing. I've had pretty good success with students that have used it. Alright, I'll post a link in the description below. So the two triangles that I show people, you've got the isosceles triangle, which gives you your 45-degree angles, and then your other triangle, which has your 60 and your 30. The shorter side would be 2. Right? Shorter side is 1. Your hypotenuse is 2, and the remaining side is root 3. Okay, just scratch that number out altogether. Hypotenuse is 2, shorter side is 1, longer side is root 3. Root 3 is a bit bigger than 1, so it has to be the longer side. And then from there, we're thinking about cos of 30, which is adjacent over hypotenuse, so it has to be root 3 on 2. Because we're in the third quadrant, we're thinking about negative root 3 on 2. Alright, so cos of 2 pi on 3, now it might be useful for you to be thinking about this in degrees. So you could be thinking about cos of pi on 3 is 60 degrees. 180 divided by 3 is 60, times by 2, which is 120. If you want to think about it in the degrees term, which can be useful for a lot of people. Anyways, diagram. All right, cos of 120 or 2 pi on 3 is in the second quadrant where only sine is positive, so cos is going to be negative again. My value will be negative, but what angle does it make with the x-axis? Well, we've got to make it up to 180, so it has to be 60. Cos of 120 is the same as cos 60, or negative cos 60. Back to the triangles, or the hand, or whatever you like to use. Cos of 60 is adjacent over hypotenuse, so cos of 60 is half. So we've got negative half in this case. Alright. So, quick recap, what we're doing is we are considering what quadrant we're in, we are considering what angle it makes, that line makes with the x-axis, wherever that is. Okay, we're looking for the acute angle, so between 0 and 90. So you don't want to say, oh, it makes it an angle with 120 degrees, because then you're back where you started. The acute angle is where our exact values come up. Alright, so 120, the rest has to be 60, and so second quadrant, negative cos of 60. Cos of 60 goes back to our exact values, or the triangles. Cos of 60 is half, so negative half is my answer. Let's do the same thing with tan of 5 pi on 4 here. I am running a little bit out of room here. 4 pi on 4 is 180 degrees, because 4 pi on 4 is just pi. We are pi on 4 past the 180 degrees, or better yet, we've actually done 5 pi on 4 as degrees, so tan of 225 get you in the same place. So we're thinking of tan of 45, alright, because it is a 45 degree angle with the x-axis, the acute angle, and because tan is positive in the third quadrant, it's just whatever tan of 45 is, which is 1, okay? And you can check that on your triangles. Tan of 45 is opposite over adjacent, okay? 1 over 1 is 1. Cool, let's move on to question 4, where things get a little bit trickier. Okay, we are solving trigonometric equations. Cos of x is equal to 0 for x is less than 0 and, greater than 0 and less than 360. So we're looking for values that we could put into here for cos, and that it becomes 0. Same as any algebraic equation that we've done before. So what angles between 0 and 360 can we put into there? Well, you can either think of the graph, okay, that's roughly it, or we can think of the unit circle. Alright, I'm personally for the unit circle, but it is up to you. If you can consider the graph, we're thinking about where is it equal to 0? Where does it have no height? That's these two values. Or, in terms of the unit circle, where is my x value 0? Remember that x is how far left or right you are. We want to be 0 left or right, so it's on the y-axis. So it is those 2 points. What is the x, or what angles do I need in order to get that situation to occur? So we've got x is equal to 90, or x is equal to 3 lots of 90, 270 degrees. If we keep going, then any further value which you could do would be outside of our domain here, so we don't include it. Alright, so that's all we need to do. What angles can we put in here in order to get a value of 0? 0 in the x-axis, 0 from the y-axis, so 90, 270. Similar idea for this part, we're looking for angles that can be sine of x is equal to negative 1 on root 2. 1 on root 2 should be one of the exact values that we are aware of. So we're trying to pair 1 on root 2 with an angle. Alright. But we're also thinking about where sine is negative. ASTC. Sine is negative at the fourth quadrant and the third quadrant. Okay, because A and S means that sine is positive and both of those has to be negative. And we're trying to think of angles between negative pi and pi that we get a value of 1 on root 2. So if we were thinking about radians for the sine of, what value do I have to put in here to get 1 on root 2? Okay, we're not thinking about positive or negative just yet. We've already done that part of our thinking. We just need to know what acute angle is involved in that situation. So you're going through, you're cycling through your exact values, or you're looking at your triangles, or you're checking your hand values, whatever you choose to do. Okay. To get 1 on root 2 by going opposite over adjacent has to be 45 degrees. So sine of 45 degrees, or pi on 4, because we actually need to use radians given that the domain is in radians, is 1 on root 2. So the angle that it makes with the x-axis has to be pi on 4. Alright. Same with this one over here. Pi on 4 has to be the angle that it makes with the x-axis in order to have that height. So in this case, we're thinking, well, I could look at my diagram. Pi on 4 is 45 degrees, so negative, because I'm going clockwise rather than anti-clockwise, negative pi on 4 is one of my solutions. Okay. If I kept going in a clockwise fashion, right, then I've got pi on 4, 2 pi on 4 is 90 degrees, 3 pi on 4, negative 3 pi on 4 is my other solution, because negative 3 pi on 4 is the angle that gets me to there, and it is greater than negative pi. If we went in the positive direction, let's just see if there's any values there. We want to see if we can meet these lines here in a anti-clockwise fashion, but less than pi. Well, you might remember that pi is 180 degrees. Anything greater than there, okay, is going to be more than pi. So we actually only have negative solutions within this domain. Alright, that's the only two there. We're going to try a trickier one where we've changed the period, okay, but we're still working in degrees, so that's going to be slightly easier. I'm thinking of values where cos is positive root 3 on 2, unit circle. Cos is positive in the first and fourth quadrant. Alright. cos of what angle is root 3 on 2? Okay, that's what I need to think about first. Go through your exact values, use your fingers, use your triangles. Where am I getting root 3 from 2 from when I'm using cos? Adjacent over hypotenuse. Cos of 30 is root 3 on 2. Okay, so that's the angle that it has to make with the x-axis. That has to be 30 degrees. And then this also has to be 30 degrees. But we are doing it both positive, so x, or 2x rather, is equal to 30 degrees. Most of a revolution besides the 30, so we've got 30 left, would mean 330 degrees. Alright, but what's going to happen is that I'm going to have to divide each of these values by 2. So just in case, maybe I add a couple extra. Full period for cosine is an entire circle, so to get back to this line again, so I've got 30, and to go around the circle completely, I've got to add another 360. So what's 30 plus 360? Well, that's 390. Right. And then what is 330 plus 360? That is 6, 90. Right. I know from practice that I can stop there, but you can keep going. You can keep adding multiples of the period and get back to the same place that you need to be. All right. So x, which is what we're trying to find, we found 2x, because once we undo what's inside the cos, we're left with what's inside the bracket. Okay, so we know values of 2x have to be 30. If I do cos of 30, then I get root 3 on 2. If I do cos of 330, I get root 3 on 2. If I do cos of 390, I get root 3 on 2. But that means that this part, the inside part of my bracket, is these values. X itself has to be half of those values. 15, 150, and 15 makes 165, almost 200, 180, 195, and 345. Now, as I said, I knew where to start because it comes from experience. A bit of practice solving your trig equations will get you there as well. But these are all the values between 0 and 360 that I can put into x and still get root 3 on 2. 15, 165, 195, and 345. You might notice that when I have divided by 2, the value that the period has changed as well. These two are different by 180, and these two are also different by 180. Okay, the period where it repeats itself was 360, but when I've divided by 2, the period's halved as well. So rather than adding a 360 to get back to the next value, I'm adding 180 instead. Anyways, it's something worthwhile remembering when we do period and amplitude changes. So, question 5. The triangle below has an area of 36 centimeters squared. Determine the value of x. Well, I have two sides and the angle between them. Okay, this is sounding a lot like my half A, B sine of C rule here. But here I've been told my area. I know it's 36 centimeters squared, and that's equal to half. A, one of the sides is x, B is the other side, is the same thing, isosceles here, sine of 30. Exact values should tell us that sine of 30 degrees is one of the values we need to be able to recognize. Sine of 30 is half. So I've got 36 is equal to half of a half of x squared, or a quarter of x squared. So what's the opposite of quarter? Timesing by 4, so I'm timesing both sides by 4, keeping it balanced. 4 times 36, 4 times 30 is 120, 4 times 6 is 24, so 144 is equal to x squared. So trying to isolate x. Okay. What is the opposite of squaring? That's the square root. So square root of 144 is equal to x. X has to be equal to 12 centimeters. Could also be at negative 12, but you can't have a negative length, so we ignore that one. And that's it for the non-calc section of the trig test. The next video will be about the calc section. Let me know if you have any questions. Bye.